So June 2020 session, Unit 6. In the first question, student investigated the conservation of the momentum using the apparatus. So student is using a glider. The air track provide a cushion of air which reduce the friction between the gliders and the track. Describe how a student would show that the air track is horizontal before starting the investigation. Like how you can make sure that this air track glider is exactly horizontal. So best way, whenever we want to show something is horizontal, what we do, we measure the distance from both ends, measure the height basically. So if we measure the height of this track, both ends, if the height is same, it means that this aircraft glider is horizontal. Like if an object or a surface is exactly horizontal, we usually measure the distance from both ends. If it is same, it means it is horizontal. The next part, the student pushed the glider A. The first light gate recorded the time T1 for the card on the glider A to pass through. The glider collided and struck another. The second light gate recorded a time for the card of a glider A to pass through. The student record T1 and T2 for three separate collisions, like three different collisions are there, and student calculated. So, like pushing the glider A, it moved towards glider B, and then they move together with each other. So, the student record the time it take to cross the first light gate and the second light gate, and using the length of a card and the time, we can work out the speed. Student record T1 and T2 for three separate collisions are there, like this is for T1 and the other one is T2. The masses of the glider were identical. If the momentum is conserved, then T2 should be equal to twice of T1. Show that the momentum was conserved in this investigation. So if the momentum is conserved, like the second time should be twice of the first one. So what you have to do, you have to compare them, like with each of the result, T2 should be equal to twice of T1. So when we take the first set of result, so T2 is how much? 0.70. And T1 is how much? 2 into 0.34, which is equals to 0.68. That is first value. When we check for the second one, like T2 is equals to twice of T1. T2 is 0.39. Twice of T1 is 0.21. When we multiply, it will be 0.39. And this will be 0.41. And the third set of a result, T2 is equals to twice of T1. So this will be 0.55. Twice of T1, that is 0.28, which is 0.56. So 0.56 and 0.55. So we have three sets of results. And when we compare the results, they don't have, approximately they are equal to each other. There's not much difference between the two values. Like 0.78 is approximately equal to 0.68. 0.39 is approximately equal to 0.41, and 0.5 is approximately equal to 0.56. So this shows that all values are consistent, results are consistent with the theory, or we can say the momentum is conserved. Another student suggests that using a piece of a card twice as long would improve the investigation. Assess this suggestion. Like you have to tell whether it will improve or no. Look, the idea or the concept is that the percentage uncertainty is equals to uncertainty. Uncertainty means the smallest value which the instrument can record divided by the value recorded into 100. So if we are measuring, like example, the student suggests that if we increase the length of the card, the experiment will be more accurate. On the glider, if we use like a twice of length, experiment will be more accurate. How the experiment will be more accurate? The percentage uncertainty won't change. The percentage uncertainty, like the smallest value which instrument can record, that is constant. That won't change. But what will happen if you use a longer, if you use a longer rectangular card? or a greater length. As a result, the time it will take to cross the light gate or interrupt the light gate will increase. So the value recorded will increase. If the value recorded increase, the percentage uncertainty will decrease. And when percentage uncertainty will decrease, the experiment will be more accurate. That is the reason why whenever we are recording a time period of oscillation, we don't record the time for one oscillation. We record the time for 20 oscillations. Why for 20? Because longer time, smaller percentage, or greater length when we measure, we have a smaller percentage uncertainty. So when you refer this like writing an answer, if you increase the length, it will, the points which you will mention, increasing a length will increase the time taken by the air track glider, like the time to interrupt the light gate will increase. If more time, longer time, uncertainty is same, so the percentage uncertainty will be reduced. As a result, it will improve the experiment or it will be more accurate. Is it clear, this one? That how the percentage uncertainty is reduced? So whenever experiment is done, we always prefer to record longer values for the same instrument rather than shorter values. Like it's the same idea. If I want to record the, say, circumference, so instead with a string, so instead of having one turn, I will have 5 turns. Because when I have 5 turns, I will have greater length, so the percentage uncertainty will be reduced. In question 2, a student wrote the following plan to investigate the distance traveled by alpha particles in air. Place a Geiger-Müller tube or a GM tube in front of a source, measure the distance d from the source, measure the count and change the d and take more reading. Devise more detailed plan of this investigation. So certain experiment, you will find this experiment is common in which you have to plan finding the range of alpha particle. Even I have shared with you that file, all the experiments are written, so you can go through there. But how we can improve this experiment, or how we can, whenever experiment is done, whenever like a experiment which is related to radioactivity, our first point we always check for background radiation. So the point here which is missing, the first point we should mention, check for the background radiation. Like radiation other than the source, we should always check, which we call as a background radiation. And the second thing, after checking our background radiation, we'll place a Geiger-Müller in front of a source, and then they should be in line. Like example, when you place a source and a GM tube is higher above, so it won't be accurate. So after placing a source in front of the GM tube, what is the next point, like extended point you will mention, like it should be placed in line with the, like source and the detector should be in line or placed in front, exactly in front of each other. Then measure the distance from a source to the tube, but you should specify how you'll measure the distance. So how you'll measure the distance between the source and the tube, by meter rule or a meter scale. And when you're measuring this distance, you should avoid a parallax error. Like looking perpendicular, or avoid a parallax error. Then we measure the count for several times, like measure a count for the several time. But this is when we place a source in front of it and we are investigating how a distance traveled by alpha particle in air, like the range of alpha particles. So what we should do when we record the counts, like measure the counts several times, and then, because this is giving a counts from source plus the background, source and background both. So then what you have to do, then subtract the background count from the total reading to get the source. So radiation from the source will be equals to the total reading minus the background counts. And then repeat the experiment with different value of D until the count, like Here they mention change D and take more average, but till what point we should take change D, because we are finding the distance traveled by alpha particle. So we will change the D until the count changes to background. So change D until the radiation or the counts reduce to background. And then for more accurate experiment, whenever you're doing an experiment, you should always plot a graph. So plot a graph between the counts and distance in centimeter or millimeter. So once the counts are constant, it means that this is a point, this is the maximum distance which the alpha particles were able to travel. Then we have only the background counts. So this is a more detailed plan of this investigation. Like answer, like reference points are there. You have to use them again just to devise a more detailed experiment. The whole procedure is given in the file which I have shared with you. It's better you also go through that file. Is it clear, this experiment? So this was a question 2 of 6 marks. Then question 3, a bar magnet was suspended from a wooden retort stand as shown. The magnet line up with the magnetic field of the earth. The magnet was given a small angular displacement from its equilibrium position and it oscillate in a horizontal plane about the string. So like first the magnet is aligned according to Earth's magnetic field. Then what we did, we disturbed this magnet slightly, like rotating clockwise or anti-clockwise, and then we leave it. When we leave, so as a result, what will happen? It will start to vibrate, oscillate between the plane. Describe how the time period of oscillation should be measured to make this reading accurately as possible. So how we can measure the time period of oscillation? Usually, whenever we are measuring it, we don't measure for one oscillation, like we measure a time for multiple oscillation, then divided by the time recorded with the number of oscillation to get the time period. And repeat the experiment or take an average. And for more because marking mean and extreme position is also another point, but where you will mark mean and extreme position, like we can use the stickers on the base of this stand. We can use a sticker like this is representing a mean position, and when we displace, this is representing an extreme position, or this one. So it's just a reference when we are looking from the top and it is vibrating in this manner. So we will have a reference point like the background reference point. So we can easily identify the number of oscillations. So point here, you will mention, record the time for 20 oscillations. Then we'll divide the time recorded by number of oscillation or by 20. Then we will repeat and take an average. And the first 2 points in which we reset the stopwatch and mark the fiducial points or mark mean and extreme position. So this is a similar experiment like how we work out the time period of oscillation for a simple pendulum. Any object which is vibrating and you want to work out the time period, you will use the same method. A loop of a wire is placed vertically around the center of oscillating magnet, as you can see. There's a DC power supply is there, and loop is placed vertically, like it's a vertical loop. When the switch was closed, the current I in the loop of a wire and the time for oscillation is decreased. The student predicted that the relation between T and I is given by this formula, where N is constant. State an additional component required in the circuit that will allow to investigate a relation. Like what student suggests, like when the current in the loop of a wire, like there's a current, the time period decreases. But you can clearly see that from this circuit, we cannot repeat the experiment. Like there is only one DC supply there and an ammeter. So what we should do, change to the circuit so that we can repeat the experiment. If I switch on the supply, maybe the current of 2 ampere is there, so it will remain 2 ampere throughout the circuit. It won't change. So how I can improve this experiment, like how we can work out that different current is passing, because we should have different values. So as a result, if what we should do, either we can use a variable supply, but what we should add to a circuit, instead of adding a variable supply, we can add a variable resistor. So when we add variable resistor, we can change the current in the circuit. So we can investigate for different values of a current, what is the time period. Explain why plotting a graph for a log t against log I would test the validity of a relation. Look, for such questions, like how we can find their inversely proportional. So how we can check the validity of the result? We have the relation that t is equals to in. So if we take log both sides, if I take log, so this will be log t is equals to log I into n. And for a logarithm, whenever like log a raised to power b is there, so when power is there, this will term as a coefficient. So it will turn as b log a. This is a log function. And same thing when log something is multiplied, like if it was log a into b, that will be written as log a plus log b. But here it's a power, so it will come as coefficient. So n is a power here, so that will turn into coefficient. So this will be log t is equals to n log I. So if this was the case, like when we compare with the equation of straight line, the equation of straight line is y is equals to mx plus c. So if I have log t and I have log n log I, and then nothing is added, so y-intercept is 0. So how we can, the question is explain why the plotting a graph so of log t and log I would test the validity of the relation. So how we test that this relation is valid? So if this relation was valid, if we plot log t on y-axis and we plot log I on x-axis, what will because this is on y-axis we have log t, on x-axis we have log I. So what will be the gradient of this graph? The gradient of the graph will be n. And this will be a straight line which will start from origin. So if this result, if this statement or this relation was valid, then when we plot a graph between log t and log I, it should be a straight line because n is constant here. As I mentioned, n is constant. So that's why we say the gradient will be constant and it will be a straight line because it does not have any y-intercept. So you will mention this point, like plotting a graph between log I and log t and log I, the gradient equals to n and there will be no y-intercept. So there should be a straight line passing through origin. If there is a straight line passing through origin, when we have these values, so it means that this equation is valid. If it's not valid, then we don't have the straight line passing through origin. Is it clear, this question? Part 2. In A levels, unit 6, usually you have a graph of logarithm rather than the direct quantities. So student processes result and produce the table. So what we need log t and we need log I. One thing you should keep in mind is that using the equal number of significant figure, like student usually like either using same number of decimal places or a significant figure. Like usually when student complete, they just write one of the value example 2, other value is 2.3, another value is 2.14. So that is not the right way of completing. Even though it is 2, write 2.00. Even though it's 2.3, but write 2.30. So you should be, when you are plotting this, you should use the same number of significant figure for both column. So you just have to use like logarithm of this and plot here, and log of 1.2 and plot like mark here. And then for all the results, you have to find the log. Then plot a graph, plotting a graph for log t against log I on the grid opposite. Plot a graph and use the additional column in the table to record the data. Then use your graph as we identify that the gradient should be n. So when this is a graph, I'm not plotting a graph as I expect from you to plot this. So after plotting a graph, you will find the gradient, and the gradient will be equal to n, because we already worked out that the gradient value for this graph should be equals to n. So what value of a gradient you will get, that will be same as the value of n. After plotting the graph, the student modified his prediction. He suggested that the relation between t and I is this, where k is a constant. Justify this suggestion. Now, how we can justify this suggestion? So again, we'll plot a graph, like we will take log. If I take log both sides, so this will be log t. This will be equal to log k plus log, like I take log and then I and n. Whenever two quantities are multiplied in log, we write them as addition. So log t is equals to log k plus log I raised to power n. And whenever power is there, it will be turned as a coefficient. So it will be log t is equals to log k plus n log I. And if I just rearrange them, so I can say log t is equals to n log I plus log k. Now we'll compare with the equation of a straight line, which is y equals mx plus c. So according to modified relation, if on y-axis I have log t, on y-axis if we have log t, on x-axis we have log I, the gradient will be equal to n. Like the gradient will be constant, means it will be a straight line, but there will be a y-intercept as well. So this graph won't start from origin, it will start above origin, because it's a positive y-intercept. So it will start above y-axis. If it was a negative y-intercept, so it will, if the question was a negative y-intercept, like this value will be negative, in that case, the graph will be like this. So how this suggestion, like to justify this suggestion, so what does it show? It shows that when we plot a graph between log t and log I, the y-intercept will be equal to log k. So this, from the graph, we can say that this graph will not start from origin, it will start above origin or from y-axis. Or there will be a y-intercept, you can also say that. Is it clear, this one? So usually the log equations are there, which you have to use. In question 4, the diagram shows a 100-gram slot mass drawn approximately to size. Determine the density of a metal from which the slotted mass was made. So the experiment is we are finding the density of this slotted mass. So state the most appropriate measuring instrument for the student used to measure the width A. So how we can measure, and the length B. So which one is the most suitable? We can use digital caliper, vernier calipers are used. Why micrometer is not acceptable here? Because there's a difference between micrometer can be used for usually external diameters. But vernier caliper is having two jaws. It is having one of the jaws, the lower jaws are used to measure the external diameter. The lower jaws of a vernier caliper for external diameters, and upper jaws of a vernier caliper are used to measure internal diameter. There are two jaws in a vernier caliper. One is at the top, one is at. So we place an object here. If you want, like example, measure a thickness, internal diameter of a test tube. So we can measure by placing it here. External. So here we want to measure internally. So the best instrument here is a vernier caliper. So for internal and external diameter, vernier caliper. Only for external diameters, micrometer, screw gauge. Micrometer is more accurate, but practically it cannot be used here as we want to measure the internal diameter. Like it's a slotted mass is there and we want to measure this part, internal diameter, this part. That's why it's not suitable. Even though external can be measured, but internal can be. Explain one technique she should use to measure A and B. Like how she can use A and B, measure A and B. Whenever micrometer or vernier calipers are used, the first step is always check for zero error. So first step, what student should do, it should check for zero error. That is the first step. Then after checking for zero error, place between the jaws and we will read the main scale and the vernier scale. And then we will repeat. Whenever experiment is there, repetition is one of the most important point. Repeat from different positions. And when we check for zero error, which error we reduce? There are two types of systematic error and random error. So when we check for zero error, we reduce the systematic error. And when we read the main scale, vernier scale, so and repeating an experiment, what it will reduce? It will reduce a random error. Calculate the area of a slot and its uncertainty in centimeters square. Assume that the slot is rectangular. So A and B values are there. We want the area. Area is length multiplied by width. Like, and we have to assume it is rectangular, this part. So area we can directly find, but how to work out the uncertainty? Uncertainty in the results. Whenever uncertainty always add. So if we want to work out the uncertainty, first we'll work out the uncertainty A, and then we'll work out the uncertainty in B, like percentage. Whenever two quantities are multiplied, then we take first the percentage uncertainty of each quantity and then add. Like if you want to work out the area, it will be A multiplied by B. That will be the area. So it will be 0.47 times 2.19. That will give us the total area of cross section, which is 1.03 and the unit is centimeter square. Now to work out uncertainty. Whenever two quantities are multiplied, we don't, uncertainty always add, but in that case, we don't add the uncertainty. We first work out the percentage uncertainty. How to work out the percentage uncertainty? So first we'll work out the percentage uncertainty in A. What is the percentage uncertainty in A? The uncertainty is the 0.01. The uncertainty in A is 0.01 divided by the value 0.47 into 100. This will give us the percentage uncertainty in A, which is 1 divided by 0.47. That's equal to 2.12%. That's the uncertainty of A. Then we'll find the percentage uncertainty in B. Percent value recorded, the uncertainty in B 0.005 divided by value recorded 2.19 and into 100. So 0.005 times 100, which is 0.5 divided by 2.19. that is 0.22%. So what is the total whenever, like, because area is calculated by A multiplied by B. So to calculate the uncertainty in area, we will add the uncertainty in A and then we'll add the uncertainty in B. So when we sum them, it will be 2.32, 2.34. This was 2.13 was there and this was 0.23. So when we sum them, it will be 2.36, or we can say 2.4%, the total. And then because we need the uncertainty in this value, like means the percentage uncertainty in area is 2.4%. So what is the 2.4% of 1.03? So 2.4 times 1.03 divided by 100. This will give us the value which is plus minus 0.02 centimeter square. So this is our uncertainty and this is the value for area. So whenever quantities are multiplied, divided, you first find the uncertainty in each value and then work out the total uncertainty. Like say a question was there, power, we want the uncertainty in power. So power is the product of voltage and current. So first we'll find the percentage uncertainty in voltage, then we'll find the percentage uncertainty in current, and then we will add to get the total percentage uncertainty in power. And then we can work out from percentage uncertainty, we can work out the value as well. Is it clear, this part? The student made a single measurement of a diameter of a slotted mass. Calculate the shaded area slotted mass in centimeter, area of the shaded area. So student measure a diameter. So what we will do, like when student measure the diameter, first we'll find, like student measure a diameter of this hole. So first what we will do, we will find the area, the total area. Area will be pi r square or pi d square by 4. Area of cross section is pi r square or pi d square by 4. We'll work out the total area, and from total area, if I minus the removed area, like the area which was removed from it, so we can work out the total shaded area. Like the total minus the unshaded, I'll get the total shaded area. So whole area minus the area of the slot. The total whole area minus the area of the slot, which we work out. And whole area is pi d square by 4 minus area of, this was 1.03. This will give us, and the diameter is given, but it's in centimeter. Yeah, it should be in centimeter because this value was also in centimeter square. So we don't have to convert. 3.14 times 3.81 square divided by 4 minus 1.03. So this will be 10.4. Calculate uncertainty in value of a shaded area. So what is the uncertainty in value of a shaded area? First, how a shaded area is calculated. We use pi d square, like we already have the and diameter, single measurement is there. So for this part, what because the unshaded area, we have to calculate the uncertainty in shaded area. So how shaded area is calculated? The shaded area is whole area minus the slotted area. Uncertainty always add. So first what we'll do, we'll find the percentage uncertainty in whole area, and we already have the percentage uncertainty or uncertainty in slotted area. We will simply even the value is calculated by subtraction, but we will add. So first, how to work out the uncertainty in whole area? So first, the whole area is calculated by formula pi d square by 4. Pi is constant, 4 is constant, so d square is there. So if d is a square, first we'll find the like how this one is calculated, the whole area, that is pi d square. So first we'll find the percentage uncertainty in d. And what will be in d square? In d square it will be double. So what is the percentage uncertainty in d? The uncertainty, because we are using a major, so this will be 0.005 divided by value recorded. Value of a d was 3.81 multiplied by 100. This will give us percentage uncertainty in d. But what will be percentage uncertainty in d square? So if what power is there, it will become like if power square is there, it will become twice. If cube was there, it will become thrice. If power 4 is there, it will become quarter, like multiplied by 4. So when we, this one, to get d square, so it will be twice. So this will be twice of this one. Why 2 is there? Because this is the uncertainty in percentage uncertainty in d. This will be percentage uncertainty in d square. And then what is the percentage uncertainty in d square? Same will be there, percentage uncertainty for area, the shaded whole area. Why? Because the area is calculated by pi d square by 4. 4 does not have any uncertainty. Pi does not have, they are constant. So all the percentage uncertainty in d square is same as uncertainty in area. So when you calculate this part, this will give you the percentage uncertainty in d square, so which is equals to 0.26%. And this slotted area, we calculated the percentage uncertainty, the total, that was 2.4%. So if this is 2.4% and this one is 0.26%, so what is the total uncertainty in this? So 2.66% will be there. So this will be 2.66 per 2.66%. That's a total uncertainty in the shaded area. And then find 2.66% of the total value. The unshaded area was 10.4. Because we need this is percentage uncertainty, we need uncertainty. So it will be the total area, which was 10.4 times 2.66 divided by 100. This will give us the value of uncertainty. So this will give us the total value for the uncertainty, like we calculated for whole area. So that is 10.4 times 2.66 divided by 100. Or you can also do one thing, like you can separately solve, like you can work out the percentage uncertainty in whole area, then percentage uncertainty already you have slotted one. So this was 11.4, the total. So 11.4 of 0.26, that will be 0.03. And this was 0.02. So when we add, it will be 0.05.